I'm Mark Cavanaugh for Cavi Coaches, and today I'm going to coach you up on impulse momentum, the quantity of motion. Today we're going to talk about impulse and momentum, and what we're going to do is we're going to look at a demonstration. So what we're going to have is two cars, one used as a force sensor, the blue one, and the red one used as in motion. Left is going to be positive, so that means right is negative. So what I want you to do is draw a force time graph from the blue car and a velocity time graph for the red car. Go ahead and pause the video and do that. So let's take a look at what those graphs would look like. So the top is the velocity time graph and the bottom is the force time graph. So let's take a little bit further look at those graphs. So let's first talk about impulse. So looking at the force time graph, let's go ahead and zoom in. It looks pretty close to a triangle, except for that little bottom part at the very beginning. So what we're going to do is we're going to define impulse using a force time graph as the area underneath that force time graph. So if we find the area using the features that we can use on the program we're using, we find that the area is negative 0.52 Newton seconds. So this is the value of the impulse. So the impulse that is imparted on the car by the force sensor is negative 0.52 Newton seconds. And we found that simply by finding the area of that triangle for the force time graph. So if we look at impulse a little bit further, we know that it's the area under a force time graph. And that area is roughly a triangle. So using the triangle area formula, 1/2 base times height, we know that impulse is going to be 1/2 the maximum force times change in time. Well, half of the value of the maximum force is just going to be the average net force. So that means that impulse can be defined as the average net force times change in time. Let's look at momentum, the velocity time graph that we created. So let's define momentum first. So it's a measure of how hard it is to stop a moving object. So let's say you have a baseball moving at 60 miles per hour coming towards you. You have a baseball glove, pretty easy to stop. If you have a car moving towards you at 60 miles per hour, not going to be as easy to stop. So what that means is momentum doesn't just depend on mass or velocity, it depends on both. So a larger object can have a smaller momentum as long as it's moving at a much slower rate. So momentum is possessed by all moving objects, and it's defined as the quantity of motion. Let's go ahead and talk about calculating momentum first. So for one particle, we can take mass times velocity to give us momentum. So lowercase p is momentum, mass times velocity, m and v, values we've used before. For a system of particles, we calculate all the individual values of the momentum, and then we would add all those momenta together. And we'd have to take into account direction as well, because momentum is a vector quantity, so it has both magnitude and direction. So let's look at calculating momentum for the car. So we have our velocity time graph here, and what we're going to use the velocity time graph for is to find the change in velocity. So we can see before the car hit the force sensor, it had a velocity of approximately 1.12 meters per second, and the velocity was in the opposite direction, but the speed was about the same, just moving in the negative direction at about negative 0.94 meters per second coming off of the force sensor. So to calculate the momentum, we're going to do mass times velocity, but we want the change in momentum. So we have the mass of the car is 0.25 kilograms, and the change momentum is mass times change in velocity. So first we're going to find the change in velocity, which is going to be our minimum, which is our final, minus our maximum. So negative 0.94 minus 1.12 meters per second gives us a change in velocity of negative 2.06 meters per second. Now we multiply the change in velocity times the mass, and that gives us a change in momentum of negative 0.52 kilogram meter per second. So let's look at impulse and momentum together. So remember that the area under a force time graph is the impulse. That was negative 0.52 Newton seconds. And doing mass times change in velocity also gave us negative 0.52, but the units are kilogram meters per second. Now these units, if you look a little closer, are the same units if we substitute a Newton as a kilogram meter per second squared. So what does that tell us about impulse and momentum? Well, those values being the same means that an impulse is simply defined as a change in momentum, as the impulse and the change in momentum in this case are both equal. So the definition of impulse is a change in momentum. So when you're asked to find impulse, we're just finding the change in momentum. So that's a vocabulary term that you're going to need to be familiar with. So impulse in equation form is net force times change in time, which is change in momentum. And a change in momentum is mass times change in velocity, which is an impulse, which means we can look at this as a big, long equation and then simplify that down to the change in momentum or impulse is mass times change in velocity equals net force times change in time. But you actually already knew this equation. You probably just don't recognize it in this form. So let's look at it a little closer, impulse momentum and Newton's second law. So let's look at Newton's second law. Newton's second law is net force equals mass times acceleration. We know acceleration is change in velocity over change in time, so let's substitute that in to Newton's second law. If we multiply through each side by change in time, we end up with net force times change in time equals mass times change in velocity. Well, we recognize this as our equation for change in momentum, the equation we just saw on the previous slide. And change in momentum is defined as an impulse. So here's our equation for impulse and change in momentum. So let's look at two objects, a big truck and a tiny little butterfly. Which one has more momentum? Go ahead and pause the video and think about it for a second. Now you probably said the truck has more momentum. Now, what if the truck's not moving but the butterfly is? So that means that we have to know more information. So if the truck is moving, by all means, yes, it's going to have more momentum than the butterfly. Butterfly probably cannot fly fast enough to have the same momentum as a truck moving, unless it's moving extremely slowly. So mass times velocity for a truck is going to be much larger than mass times velocity of a butterfly when both objects are in motion. But we need to know if they're both in motion. Otherwise, the truck would have a zero momentum if it's not moving, and the butterfly would have a larger momentum than the truck. Let's go ahead and recap impulse and momentum. So we know that the area under a force time graph is the impulse. Momentum is a measure of how difficult it is to stop a moving object. We used the baseball and car example. Impulse is defined as a change in momentum. So when you're asked to find impulse, you're just finding a change in momentum, and that can be found one of two ways. Either by doing change in momentum is mass times change in velocity. And in this case, when we're finding momentum, the velocity defines the type of momentum. An initial velocity would be initial momentum. Final momentum would be calculated using final velocity. A change in momentum would be a change in velocity. So impulse, we know, is defined as net force times change in time, but an impulse is also a change in momentum. So that means change in momentum can also be calculated using net force times change in time, which gives us our rearranged version of Newton's second law, which is mass times change in velocity equals net force times change in time. So this is an intro to impulse and momentum. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.